Something
Terrible.
happened a year ago, during the summer of 2023. Now, I'm sure that you can remember the tragic events that unfolded when OceanGate submersible Titan went missing during its descent to the remains of the Titanic. I can still vividly remember how the world held its breath once the news had broken. The news made headlines around the world.
The latest now on the tragic end to the search.
And everyone started to speculate. What do you reckon happened to the submersible? Are the millionaires still alive? And you know what? Only James Cameron, it would seem, knew that the submersible must have imploded, killing everyone on board within a fraction of a second.
And got confirmation that there was some kind of loud noise consistent with an implosion event. That seemed to me enough confirmation that I let all of my inner circle of people know that we had lost our comrades, and I encouraged everybody to raise a glass in their honor on Monday. Then I watched over the ensuing days this whole sort of everybody running around with their hair on fire search, knowing full well that it was futile.
Now, how did the director of Titanic know that? Well, through extensive experience. He's a legit deep-sea explorer. I mean, if you haven't seen his documentary, Ghosts of the Abyss, it's definitely worth watching. Now, aside from his experience, James Cameron also has a working understanding of material science. History, as we know, has a way of repeating itself. But this time, though, the fate of the Titan unfolded in the way it did due to an iceberg of colossal underappreciation for the insidious nature of polymeric corrosion. OceanGate constructed their submersible from really unsuitable materials. The hull was composed of carbon fiber reinforced epoxy composite, which is an incredibly stiff, rigid material. It's a material that we're familiar with as dentists. It hit the market back in the 1990s. That was when fiber-reinforced composite posts were introduced as an alternative to custom-made post and cores. But these early versions of carbon fiber posts were met with sighs of disapproval from dentists because they were black. The posts, I mean.
But you're black.
Just to be clear, the posts were black in colour, which resulted in poor aesthetics if used under a ceramic restoration. And they were also insanely stiff, way stiffer than the dentine, which posed a risk of fracture for the tooth. Dentists will be all too familiar with the limitations of polymer-based composites. They corrode given enough time, and when you add unfavourable conditions to the mix, the process is only exacerbated. So think about the hull of the submersible and everything it was exposed to. Immense pressure, hydrolysis by the ocean water, which also fluctuates in pH and temperature. And bear in mind that the end caps of the Titan, they were made out of titanium. Now, metals and carbon-reinforced polymers have different bulk moduli. Polymers are more compressible than metals are. And those end caps, made out of titanium, they were glued onto the hull.
Really what's holding them together and allowing them to move together is the glue.
The glue's very thick, so it's not like Elmer's glue. It's like peanut butter. Oh yeah, so that will be the pressure vessel for Cyclops 2. It'll go to 4,000 meters.
So that region of the submersible may very well have been the weak link where the breach occurred. Or, I don't know, who knows, maybe it was a pinhole leak that occurred in the polymer-based hull. It doesn't matter. In either case, at those depths, water is compressed. So even if there's the tiniest breach in the hull, it will decompress and fill up with water faster than the speed of sound. So tragic events like this only highlight how important having a comprehensive understanding of material science is. So with no further ado, as the curator of Isle Ivory, let's kick things off and start looking at the basics of metals. broadly speaking, dental materials can be divided up into three main categories: ceramics, metals, and polymers. Yeah, there are outliers, absolutely. Materials that don't fit snugly into these broad categories like, I don't know, wax and gypsum, but this is nevertheless the core, the trinity of dental materials. Now, each part can be broken down further into all manner of different kinds of subcategories. But let's just dwell for a moment on that notion of breaking something down. Breaking something down, splitting it in half, making something smaller. So let's say I have a lump of metal and I cut it in half with my sword. It's a really sharp sword that my dad gifted me in an amphitheatre in Joppa. So yeah, I cut the metal in half and then I just cut it in half again, and I just continue to just hack away at this piece of metal until I get ever smaller and smaller pieces of it. Now the Greeks, the ancient Greeks, they had a word for this, you know. This thought experiment's been around for a while. Democritus used the word atomos to describe the smallest part of any physical thing. And that's where we get the word atom from. Atomos means indivisible. Now we know quite a bit about the atom nowadays. It's not in fact the smallest indivisible component of physical matter. An atom is actually comprised of subatomic particles. Up and down quarks are the building blocks of protons and neutrons, both of which can be found residing in the nucleus, and whizzing around said nucleus are the negatively charged electrons. And it doesn't stop there. Apparently you can keep on going once you're in the quantum realm. Turns out that the fabric of the universe is made up of strings, small strings of dental floss vibrating away to the cosmic dance of infinity. Something like that. Theoretical periodontology isn't my thing. I don't like calculus. Anyway, where were we? Atoms. Yes, atoms are commonly believed to be the smallest part of physical matter. Which isn't true because of subatomic particles. But you know what? Let's run with that misconception of atoms being the smallest part of matter for a moment anyway. All right? Because everything depends on the kind of matter you're talking about. Imagine you're about to cut into a piece of chocolate. You've just bought your airport Toblerone and you're about to cut an Alp into smaller and smaller pieces. All right? You will never, ever get a single atom of Toblerone. Trust me. Elements represent the purest and most fundamental forms of matter, with atoms being their smallest constituent units. The differentiation between atoms of different kinds of elements that you can find in the periodic table lies primarily in the number of particles that they contain. So take gold, for instance. Gold has an atomic number of 79, so that signifies that within the nucleus you can find 79 positively charged protons, and within the electron cloud you can locate the position of 79 negatively charged electrons. Don't ask me what their velocities are though.
Say my name.
Now these opposing charges from the electrons and the protons, they nullify each other, which makes the gold atom electrically neutral. Now in this picture we can see a lot of gold. Gold rings, Cartier bracelets, gold day-date, that's nice, and even gold teeth, not as nice. Now, gold has historically been a very popular dental material. Now, nowadays it's used much more infrequently. It's hard to compete with cost-effective options like base metal alloys and ceramic materials. Now, despite gold being prohibitive for obvious reasons, it still maintains its reputation as being a fantastic dental material. So let's try to understand why that is. It's time now to zoom into Post Malone's grills. And if we zoom in close enough and use our imagination, we can picture gold atoms all neatly arranged. And just to be clear, the gold spheres represent the positively charged nuclei of gold atoms. But what keeps the atoms bound together in a neatly arranged crystal lattice? Metallic bonds. Metallic bonds are the electrostatic forces of attraction keeping it all together. Now this works because the valence electrons of metals, i.e. the electrons in the outermost shell, are able to delocalize and move freely throughout the metal's crystal lattice. This isn't like the sharing of electrons between two atoms in a covalent bond. No, it's not like that. The delocalized electrons are not tightly bound to any specific atom. They're shared by the entire collective of atoms, so to speak, all contributing and sharing as best they can, making metallic bonds communist, now I think about it. Yeah, so the sea of delocalized electrons is able to flow through the lattice and create a conductive pathway, giving metals their characteristic properties like electrical conductivity and mechanical properties like ductility and malleability. Let's just unwrap that, okay? Metallic bonds and crystal lattices actually impact the mechanical properties of gold. Now, I'll show you how by deforming the atoms in this lattice. All right, so let's zoom out now, and I'm going to change the shape of the lattice by deforming it. And I'm going to deform the two upper rows of atoms, but as I do so, I want you to focus on these two atoms that I've highlighted in blue. Watch those two atoms closely now as I deform the neatly arranged lattice. Right, so notice what happens as I apply the force and deform the material. The two upper rows of atoms glide slightly to the left, resulting in what's known as elastic deformation. The moment I remove the force, the atoms spontaneously return to their original position in the crystal lattice. So an elastic deformation is not permanent. The change in shape was not permanent. The material snapped back into its original shape as soon as the force was removed. Think of an elastic deformation like you're stretching the metallic bonds. You're not applying enough force to break them apart, which means that everything rebounds back to the way it was once the force disappears. All right, now let's apply an even larger force. Let's put some distance between those two blue atoms. Now I've deformed the material beyond its elastic limit, breaking metallic bonds in the process, and watch what happens now once I take away the force. The gold atoms don't return to their original position. This is plastic deformation, a permanent change in the shape of the material. It's thanks to the shared sea of delocalized electrons that gold atoms are able to form new metallic bonds in this new position. Now, this entails that gold is relatively pliable. It can be bent, twisted, or stretched into various forms without breaking. Gold exhibits malleability, which refers to its ability to be flattened under compressive forces. Using a hammer, it's possible to transform a lump of gold into a wafer-thin sheet. Gold is also known for its ductility, a property that enables it to undergo significant plastic deformation without breaking, without fracturing. So when subjected to a tensile force, this lump of gold can be stretched and elongated into a wire. In contrast, materials that lack pliability, that are on the other end of the spectrum, so to speak, can be referred to as being brittle. Brittle materials will fracture once you pass their elastic limit. That is to say, a brittle material will not undergo a large amount of plastic deformation. Glass is a great example of something brittle. Glass is structurally amorphous. It doesn't consist of a crystal lattice, and if you apply a large amount of tension, it breaks apart, it shatters. Right, so I've already mentioned crystal structures. I've used the term lattice when describing the structure of gold. A crystal lattice is quite simply a very highly ordered repeating pattern of atoms or molecules. It's important to note that crystal structures are not exclusive to metals. Polymers and ceramics can also exhibit them. If you want to create a crystal lattice, you need to start with the smallest building blocks. It's a bit like Lego in the sense that you can build something really complicated like Hogwarts just from simple building blocks. Now, in reality though, a crystal lattice that we might find in a metal is composed from a simple building block called a unit cell. Here we have a model depicting a simple cubic unit cell. The yellow balls represent atoms and the sticks connecting them are the bonds. It's not particularly accurate when we consider the nature of metallic bonds, so a model like this is somewhat better, but it's not ideal. It's actually quite misleading because how many atoms are located within a simple cubic unit cell? 8, right? There are clearly 8 atoms in the model, but no, the answer is actually 1. There's only 1 atom located in a single simple cubic unit cell. This model is far more illustrative. Only 1/8 of each and every atom is actually located in the corners of the cube. So 8/8 of an atom that reside within the cube give us 1 atom in total. Now, once you wrap your head around this, you can begin to appreciate that each atom within the lattice has the potential of occupying 8 different unit cells at the same time. It's almost like the atoms split itself up into 8 parts, making it more evil than Voldemort. Remember, he only did it 7 times. So material science is like the dark arts of dentistry. Don't forget that. And that's why you know you love it. The simple cubic unit cell is, bear in mind, just one subtype within the family of cubic unit cells. Here they are, see? And we're going to take a closer look at them in a moment. But notice how many different families of unit cell types that can exist in nature. Now, the most relevant ones for us as dental folk, the ones that we need to be a bit more familiar with, are the cubic, hexagonal, tetragonal, and monoclinic unit cell variants. But for now, let's just take a look at the basic ones, the cubic subtypes. The simple cubic, we've already addressed this one, 8/8 of an atom and all of that. But the next one is called the body-centered cubic unit cell. And this one has an entire atom chilling in the middle of it. So in total, there are 2 atoms within this subtype. The face-centered cubic unit cell has the same starter ingredients as the simple cubic with 1/8 of an atom in each corner, but it also has half an atom on each side of the cube, giving us a grand total of 4 atoms. In the cubic family, different types of atomic packing lead to varying levels of density. So for example, the face-centered cubic unit cell contains more atoms packed tightly into it compared to the simple cubic structure. Now, this distinction is important because the number of atoms and their arrangement within the unit cell can influence the ease of slip, which refers to the smooth gliding motion of atoms past each other when the metal undergoes deformation due to stress. This process of slip doesn't just occur haphazardly. We're going to take a look at this YouTube video of a simple cubic unit cell that forms this lovely crystal lattice, and when a force is applied to the lattice, plastic deformation can occur. And this is best understood within crystallography by the concept known as slip systems. Basically, the atoms within the lattice form slip planes, planes of atoms that can slip or glide past each other. Now, these slip planes can slide past each other in different directions, which is known as a slip direction, obviously. Let's look at this animation that's going to help clarify the concept. On the left, we can see 3 different layers of atoms that are stacked on top of each other. Each one of those layers is a slip plane. So there's a red slip plane, a blue one, and a green slip plane. Now let's draw our attention to the upper slip plane, the green layer of atoms. The green slip plane can undergo plastic deformation by sliding in relation to the lower layers that remain stationary. As we can see, the green slip plane is able to slide laterally from left to right. It can also glide at an angle, obliquely, diagonally to the right, and in this example it can even glide diagonally to the left. So in total there are 3 different slip directions. A slip system is therefore the number of slip planes multiplied by the number of slip directions. Now, take note, because very few metals have a simple cubic lattice structure, and that's because it's not the most efficient way to pack atoms closely together. Metals typically adopt more densely packed structures, like the face-centered cubic unit cell structure, which we can see here. And from now on, I'm going to refer to it as FCC to save time. Now, as you can see, all 4 unit cells are FCC. And the yellow triangle within each unit cell represents the orientation of a slip plane. So there are 4 different potential slip planes within a FCC unit cell. Now the black arrows on each triangle, yellow triangle, indicate the slip directions. Each slip plane has 3 slip directions. So 4 slip planes times 3 slip directions gives us a grand total of 12 slip systems for metals like gold and copper, because they're metals that are made from FCC unit cells. 12 slip systems is a lot relative to other types of unit cells.